It begins as solid, unyielding stone, yet its final form is a delicate cloud of fiber. The transformation of rock into wool is a feat of modern engineering, with global production generating over 8 billion square meters of this material each year. This vast quantity is destined to insulate and soundproof millions of buildings across the globe. The question of how these inert chunks of earth are spun into one of our most effective thermal barriers is a compelling one. The answers are forged in fire and force deep inside the world's largest mineral wool factory, where this industrial alchemy unfolds on a colossal scale. In a land forged by fire, a goddess's fury gave birth to a delicate shield. Roughly 1,000 years ago, across the volcanic Hawaiian Islands, streams of molten lava were caught by the wind and stretched into fine, thread-like fibers that intertwined to form a natural insulating blanket. Legend tells that these were the very hairs of Pele, the goddess of volcanoes, torn from her head during a furious eruption. For generations, native Hawaiians gathered this sacred material, using the gift of nature to protect their homes from the elements. Then, in the early 20th century, a group of scientists rediscovered the extraordinary insulating properties of this volcanic substance. From that knowledge, the modern material known as Rockwool was born. But the lava of Hawaii could never satisfy the demand to insulate millions of houses. The forces of nature had to be recreated through industrial processes, a solution that would come with its own environmental costs. In the United States, states with immense basalt deposits, such as North Carolina, Missouri, and Utah, became the new primary sources for large-scale rock wool production. The earth trembles not from a natural quake, but from a deliberate, calculated force. This is the genesis of rock wool, a process that begins with the very bones of the planet. Stone, specifically basalt and dolomite, are chosen, hard, resilient minerals prized for their ability to endure immense heat and for the essential compounds locked within them. In the vast open-pit quarry of Cardinal Aggregates in Ohio, a staggering 700,000 tons of this stone are unearthed annually. The first task is to peel back the Earth's skin, as giant excavators and articulated haul trucks strip away the overburden. This soil is carefully stockpiled, destined for resale or to heal the land once the work is done. With every 10-foot section of dirt cleared away, approximately 1,600 tons of raw basalt are exposed to the sky. From here, the process turns to brute force and precision. Powerful drill rigs bore into the solid rock at a rate of nearly 5 feet per minute, carving out a precise grid of shafts that map the blasting zone. Under the watchful eyes of blasting engineers, between 15 and 30 of these holes are meticulously loaded with explosives. Each charge is sealed and wired into a firing system, ready for the signal. A single thunderous blast can fracture between 15,000 and 25,000 tons of raw stone in an instant. The shattered rock is then hauled toward the crushing plant, where massive jagged blocks are systematically broken down into fragments smaller than 10 inches across. This initial crushing is just the beginning, as the plant continues to refine the material, ensuring it meets exacting technical specifications. Before being loaded, every single bucket is electronically weighed for accuracy. On the busiest days, a constant stream of over 400 truckloads will depart from the quarry, a fleet delivering between 8,000 and 9,000 tons of processed stone each day to manufacturing facilities. It is from these very blocks that solid rock will be reborn as millions of fine mineral fibers, the foundation of modern building insulation. Solid stone arrives by the ton, only to be reborn as something lighter than air. The journey begins as a procession of heavy-duty trucks, laden with basalt from the quarry, rumbles into the plant's receiving area. As metal gates slide shut, clouds of dust billow upward, and the raw stone tumbles onto conveyor belts in a thunderous cascade. Under the factory's cool blue glow, the gray boulders flow into storage hoppers, a steady stream of rock. Stones of a uniform size are sent directly to the processing line, while irregular chunks and impurities are diverted down other conveyors toward the crushers. On the batching conveyor, glossy black particles of coke are sprinkled evenly into the stream of basalt. This addition of coke provides the intense heat needed for the furnace, but it also alters the chemical composition, allowing the basalt to melt more quickly and uniformly. From there, The mixture is fed into a colossal furnace where temperatures soar above 5,100 degrees Celsius. In this inferno, the materials dissolve into a glowing red river of lava, a thick liquid rich in silica, alumina, calcium oxide, and magnesium oxide, nearly identical to volcanic magma. Sparks fly in all directions as the molten current pours forth, and workers clad in ceramic fiber suits and metal masks step forward to monitor operating conditions. The channels and pipes guiding this fiery sea are forged from heat-resistant steel and lined with special refractory bricks. These furnaces operate non-stop, 24/7, as a shutdown would not only consume immense energy to restart, but also shorten the life of the lining and risk lava solidifying on the walls. The stream of molten rock is then directed onto high-speed spinning wheels. As the incandescent liquid strikes the rotating surfaces, it is flung outward, stretching into fibers thinner than a human hair. A simultaneous blast of hot air follows the spin, carrying the fibers away and cooling them rapidly in midair, locking their slender, durable forms into place. The result is a gentle rain of mineral fibers, settling into a light, fluffy mat with extraordinary heat resistance and sound-absorbing properties. The newly formed rock fibers are immediately collected, carried by a current of hot air, and deposited evenly onto massive rotating drums or wide conveyors. Layer by painstaking layer, the fine strands accumulate, forming a continuous blanket of mineral wool that stretches down the line. Powerful fans and suction ducts are carefully calibrated to ensure the fibers are spread uniformly, preventing any thick or thin spots from developing. At this point, the material is still soft and ethereal, resembling a flowing sea of white fibers moving along the conveyor. The rock wool now exists in a block-like form, but the initial streams are only a few centimeters thick, so they must be continuously layered to achieve the desired size and density. The flow of rock wool proceeds to the layering stage, where mats are stacked one atop another, building the sheet's depth from a few centimeters to as much as 20 to 30 centimeters, depending on its final use. Conveyor belts move in a steady rhythm, ensuring each layer is spread evenly without leaving gaps. After being layered, the mat advances into a massive roller press system, where uniform pressure is applied across its entire surface. This compresses the loose fibers into a sheet of precise dimensions. The rollers are calibrated for each product. The thinner and denser the final sheet, the greater the pressure applied. Simultaneously, mechanical arms press repeatedly against the sides, keeping them tight and preventing the material from spreading. The result is a firmly compressed block of mineral wool with a uniform thickness of about 8 to 12 inches. Once compressed and stabilized, the block moves through a high-speed cutting system. Blades trim away the excess material, creating straight, squared sides that conform to the desired mold shape. As the block continues down the line, additional cutters descend, slicing the thick blanket into individual panels, each with identical dimensions. Sensors monitor every cut, ensuring length and width remain consistent from one piece to the next. By the end of this stage, the once loose mat has been transformed into neatly shaped insulation boards. Each block is cut into standard panels, typically around 24 by 48 inches, with thickness ranging from just a few inches for residential use up to nearly a foot for heavy industrial insulation. The rock wool slabs are now formed, but must pass a crucial stage of quality testing. This includes a hardness check, where pressure tests confirm the slabs can endure mechanical stress without losing their shape or density. And since mineral wool is valued for being both fireproof and insulating, a fire test is essential. A flamethrower blasts the surface with temperatures around 1200 degrees Celsius, while a person can sit directly behind it, completely unaffected. After inspection is complete, the insulation boards are carefully wrapped in heavy-duty plastic film. Automated machines seal each block, protecting it from moisture and damage during transit. The packages are then secured with an additional layer of shrink wrap to keep them stable when stacked. Forklifts transport the finished bundles to tall warehouse racks, where thousands of units are stored in neat rows. Finally, they are loaded onto trucks and shipped to construction sites, factories, and projects across the market. At a job site, the panels are fitted directly into pre-prepared wooden or metal frames. Workers cut the panels to size and press them firmly into the cavities, ensuring no gaps remain. Thanks to their interwoven fiber structure, the panels hold themselves in place with minimal need for adhesives. This hidden layer becomes a protective shield, keeping buildings warm in winter, cool in summer, and safer from fire. A similar alchemy, turning humble minerals into advanced insulation, begins at a different batch plant, where another set of raw materials is stored, ready for its own transformation. It begins with the grit of sand and the shimmer of shattered glass. From these hard, unyielding elements, a substance as soft as wool will soon emerge. The journey starts where the raw materials are first delivered and stored. The main minerals include sand, soda ash, borax, and dolomite, but the most crucial ingredient is recycled glass, or cullet, which makes up nearly 80% of the furnace feed. This material is sourced from two streams: plate glass from windows and windshields, and container glass from bottles and jars. Trucks pneumatically unload everything into storage silos, holding enough material to keep production running for 4 to 5 days. When the furnace signals its need for a batch, an automated system precisely weighs each raw material and blends them into a complete mixture. This blend then travels by conveyor, lifted to an upper level where it is held in a feeder silo right next to the furnace. This reserve contains enough material for about 8 hours of operation, giving the plant a crucial window to react if any issues arise in the batch line. From the feeder silo, the raw mix descends straight into the heart of the process, the glass melting furnace. The materials are fed through a water-cooled screw conveyor into the massive chamber, which combines gas-oxygen firing with supplemental electric resistance to deliver both power and environmental efficiency. Inside, molten glass boils at around 1400 degrees Celsius, with flames sweeping across the surface, while electrodes remain submerged beneath the melt. From here, the glass streams through heated channels that maintain the exact viscosity needed before it can be spun into fibers. The molten glass flows into a spinner rotating at an extremely high speed, shooting out through thousands of tiny holes to form a cascade of ultrafine fibers. A stream of hot air blows downward to stretch them, while compressed air helps control their length and assist with cooling. The first spray ring uses only water to lower the temperature, while the next coats the fibers with a proprietary binder, an exclusive formula that is both colorless and free of formaldehyde. The glass fibers are collected in a forming chamber and spread evenly onto a conveyor belt, creating a continuous, wool-like mat. To ensure uniform density across the entire surface, a cross-distribution system moves back and forth. Freshly spun fiberglass is naturally off-white, appearing light and fluffy as it rests on the conveyor. A liquid binder is then sprayed on, which looks clear at first, so the mat stays white. But after passing through the hot curing oven, the binder hardens and turns yellow, orange, or pink, depending on the specific formula. The soft, fluffy mat is first compressed under heavy rollers, transforming it into a firm block with consistent thickness and density. This step locks the fibers together, making the material much easier to handle in the next stages. The compact block then moves into the cutting line, where sharp blades slice it into panels of precise dimensions, and guides ensure every sheet has a uniform size, ready to meet building standards. Finally, the panels are wrapped in protective film and tightly sealed to guard against moisture and damage during transport. Forklifts stack the bundles onto pallets, which are then loaded onto trucks for delivery to warehouses and construction sites nationwide. In the United States, one company's pink fiberglass insulation covers most of the market and has become its signature look. They even went so far as to trademark the pink color, making it legally theirs. One is spun from ancient volcanic rock, the other woven from delicate threads of glass. These are the two most common insulation materials found across the globe: Rockwool and fiberglass. Within the walls of our homes, they serve as unseen guardians against the extremes of every season. Each material is engineered to keep our living spaces warm during the biting cold of winter and to offer a cool sanctuary from the oppressive heat of summer.